Right. So the way we will probably do entanglement, I don't know. I think I did talk about entanglement, right, before? Yeah. So today we will. So I think I did talk about entanglement a little bit. So first, let me do a small mathematical expression of this, and then we will try and understand the intuition, and then we will do the Bell's inequality. We'll try and understand the Bell's inequality. That's what is the important thing. Okay, the Bell's inequality experiment. John Bell. So that's what we'll do. Okay. So simply saying, let us imagine this. I think last time in the introductory class, I just said you can do a C naught and a Hadamard and a C naught, and you can entangle two particles. That's what I said. But essentially, what does it mean? Okay, that is one implementation. Of course, there are many other implementations you can talk about. Let's talk about two particles. Okay, let's talk about particle 1, or maybe call it qubit 1. Maybe that's better. Maybe simply, if I say it like this, maybe there is a qubit 1 and there's a qubit 2. Okay, and let us say this can reside in two states. Let's say U1 and U2. Okay, and this be, let us say, in V1 and V2. Some states, right? Some two states. This has two states, U1 and U2, and so basically, what does it mean? If you to write this, you can say qubit 1 is in some state, right? Alpha 1 U1 plus alpha 2 U2, right? This you can describe as the superposition state of qubit 1, correct? Where alpha 1 and alpha 2 are the amplitudes. The probability is proportional to alpha 1 square, alpha 2 square, the modulus, right? Correct. So this is what you can think about. And similarly, you can say qubit 2 is nothing but, you can say, I don't know, beta 1 V1 plus beta 2 V2. Some state like this. Correct. So now, if you want to understand, if you want to write the combined state of these two qubits, right? This is the superposition state of qubit 1 and this is the superposition state of qubit 2. Right? So now if you want to write it down as the combined state of those two qubits, right? You want to write one configuration, which is the combined state. That is nothing but the tensor product of the two states. That's what we talked about in the introductory session. So that just becomes alpha 1 U1 plus alpha 2 U2 tensor product beta 1 V1 plus beta 2 V2. This is what it is. This is the tensor product of those two. This is the combined state of those two qubits. Okay. Maybe we want to simplify this because it becomes useful. Maybe I will simplify it at the top, because otherwise this will. If you simplify it, what does this become? This becomes something like alpha 1 beta 1 U1 tensor product V1, right? Plus alpha 1 beta 2, same thing, alpha 1 beta 2, this is what, U1 tensor product V2 plus alpha 2 beta 1 U2 tensor product V1. Plus alpha 2 beta 2 whatever. Okay. So this is the most generic state that you can write. Two particles, each qubit with U1, U2 and V1, V2, alpha 1, alpha 2, beta 1, beta 2 being the amplitudes of those of those states, where where basically your alpha 1, alpha 2, beta 1, beta 2 are complex numbers, right? Or some complex numbers. So this is the most generic way of writing the state of 2 qubits. Similarly, you can write the state of n qubits if you want. Okay, you generalize it to n, you will get n qubits here. Now, let's just keep this in mind 1 second and let us do something else, and then we will see what does it mean for 2 particles to be entangled. Now let us say there is a real state of some particle, okay, which is just U1, V1 plus V2, U2. U2. Let us say this is the state of a particle. Actually, this is the most general state. Let us say this is one actual state of a particle. So for this to happen, what should happen out of this? Alpha 1, beta 1 should be equal to 1. Correct? Yes. Alpha 1, beta 2 should be 0. Correct?
Yes.
Similarly, alpha 2,
beta 1
so 0. And alpha 2, beta 2 equals 1. Correct? This is what you need for this to happen. Correct? Yes. But this is impossible. Correct? Because if alpha 1, beta 2 equals 0, then alpha 1 has to be 0. But alpha 1, beta 1 is equals 1, so alpha 1 cannot equal to 0. So if you see this equation, this is impossible. Correct?
Yes.
So you cannot write it as some state of particle Q1, Q2. You cannot factorize this like this. However you factorize, both will be there in each. You cannot factorize. So these 2 particles are entangled, right? That is what it means mathematically.
So the state where
it's a very funny state.
The state where we cannot factorize.
You cannot factorize. You cannot factorize. See, entanglement can be understood as entanglement between n particles is such that their combined state cannot be factorized into individual states. So where every state is dependent on something else also. So for example, this is dependent on the first qubit and second qubit state also, V1 also. Similarly, V2 and U2 and V2 both. If you could factorize it only among U1, U2 and V1, V2, then they are not entangled. Correct. So that is the way, mathematically, that is how you define entanglement. Okay. It is a very funny state. Actually, it is kind of, there is no classical analogy to that. You cannot understand this. In fact, before I go along, let me just tell you one thing that is very, I'll give you a 10-second spiel of entire classical physics. See, entire classical physics you can simply understand in one simple way. Let me do that. Maybe that will help you understand entanglement a little and why this is so funny, right? So let's say there is, we are digressing into classical for just a second, okay? So just a second. You're right. Let us say these are 4 states, 4 configurations of some classical particle. Okay. What do I mean by configurations? Classical particle. A configuration can be simply seen as, let us imagine this to be the position of some particle. Okay. In whatever dimensional space, 2-dimensional space. So these points are not points in space. These are configuration spaces. What does that mean? That means let us say point is, let's say there's an XYZ. Okay, and let us say the point initially is in, let's say this is point A, point whatever, one point, which is initially in the place 0, 0, 1. Okay, then another configuration of this could be, I don't know, 0, 1, 0, and another configuration could be something else, right? 1, 0, 0. Another configuration could be 1, 1, 1. Another configuration could be 0, 0, 0. So these are all the different configurations of where the particle is. Now, this is position. You can call it temperature. You can call it momentum. You can call it energy. Anything. See, in all classical physics, what do? You finally take a configuration of something, and then you have laws on how to move it from one configuration to another configuration. If it is a particle, those are movements of laws of motion. If it is electricity, it is the laws of electricity. If it is light, it is the optical light. But finally, what you have some state, which can be described by a configuration, and you have talked about a movement to another state. Right? Entire classical physics can be just explained in that 2 sentences. That's all that there is, finally. In fact, quantum can be described in even less. So let us imagine you have something like this. Let us have, so these are the 4 configurations or 4 states of some particle. Okay. And these are the laws governing how it moves from one configuration to another. You can kind of number it if you want, 1, 2, 3, 4, or whatever. Okay. Now, what is the problem with this diagram that I have put? If I have put it like this, it means if you are at particle 2, for example, okay, you are at particle 2, you are at this state, you are in this configuration. You know where to go next, but you don't know where you came from. You could have come from 1, you could have also come from 4. You don't know where you have come from. Is this clear to people on the phone? Are you guys following what I'm trying to say here?
Yes.
Yes. You don't know where you want to go. So in this case, your past is not fixed. Your future, you know where to go, but the past is not fixed. Classical physics doesn't allow this. You cannot have it. In entire classical physics, both past and future are reversible. If you are at any given state, you should know what state you came from, and you should know what state you will go into. Both. Similarly, if I change this arrow also, it's a problem. This also is not a problem.
You have to know where to go.
You have to know where to go. Here, future is not reversible in that sense. Okay, because you are at 2, now you are confused. Should I go to 2 or should I go to 4? Both are there. Now, this is the entire classical physics can be simply explained by this. All classical physics, whatever laws you have to obey this rule. In fact, there is no law in physics that does not obey this. Everything is time reversible. It's not only time, even in space or in time or in symmetry or in anything, it has to be reversible. Reversible meaning not reversible in the sense of that the process has to be reversible, but you should know where you came from and you should know where you need to go to from any state to any state. Whatever laws you write, this cannot be hindered. This is the holy grail. In quantum physics, as we kind of see, this is broken. And that's actually the big difference. The biggest difference, if you say, is essentially that. That's what entanglement means. That's what superposition actually means in all states at the same time. What does it mean to be in all states in the same time? It doesn't mean anything actually. So similarly, entanglement has no classical analogy that I can give you, because in classical world, this is not allowed. We will see a Bell's experiment today, which is a very, we'll see the genius of John Bell today. Okay, in terms of why John Bell is considered such a genius in quantum physics. Okay. So now, what does this mean, right? So let's first talk a little bit about EPR paradox. A little bit about EPR paradox and why Einstein got completely mad at at this sort of nonsense that kind of happened, right? So the previous equation that I wrote, what does it tell you? It tells you U1 tells you something like this. U1 tensor with V1 plus U2 tensor with V2. This is entangled. So what does it mean now? For a second, imagine this. Imagine it is simply spins. Okay, imagine we're talking about spin. Now what is spin? Spin of an electron or spin of a photon is not that it is really spinning. Okay, but an electron has angular momentum. There is a component of angular momentum. Okay, because it has a component of angular momentum that we can measure, we call that spin. It's just a name given. Spin is just two directions. This is how it's denoted, either spin up or spin down. We'll talk a lot about spin because we'll talk about.
Atomic structures have 4 types of quantum.
Exactly. So, but the problem is, don't think of spin like it's a top spinning. Nothing spins, but these particles have some angular momentum. So if you think about it like that, you can, what you can write here, you can write something like, let us say U1 and V1 are up and U2 and V2 are down. Correct? So both have up and down. So if you kind of say that, what do you say? This is basically U1 tensor product V1, which is again another up. Okay, this is for particle Q1, this is for particle Q2. Plus, you are saying some down state, tensor product, some down state. This is again for Q1, this is again for Q2. So this is some state you are talking about. You are talking about two electrons with two states and each one has a spin up and a spin down. Now, what is the problem here? The problem is angular momentum is conserved in the universe. Right? So the angular momentum is conserved. You cannot have non-conserved angular momentum. Actually, this is wrong. It has to be this way. So we will have to make them different. So when I say U1 and V1, no, it will be U1 will be top and U2 will be bottom. It has to be like that because you cannot write a state like that. So it has to be like not U1 and V1. It has to be U1 and this U1 equals if U1 equals top, U2 has to be bottom. Similarly, if V1 is this, then V2 equals this. Okay, so this is not right. Sorry about that. Okay, so this is not right. So if you have a state like this, what does this mean? This basically means if you measure, if somebody who has qubit 2 measures and that turns out to be positive, then automatically qubit 1 has to become down. Okay, the spin has to be down because once you measure and this comes up, Q2 becomes up, this is ruled out, right? Because here there is no up in Q2. So this comes, so it means the answer has to be this and this has to be down. So as soon as you measure Q2, instantaneously Q1 has to be measured. Like their states are entangled. So this is what entanglement tells you. This is what mathematically it tells you in quantum theory, okay, quantum mechanics. Now, what was the problem that Einstein had with it? Einstein's problem was he kind of said that if this is actually true, it is not just Einstein, it's Einstein, Podolsky, and Rosen, all three of them. And what they essentially said is, now if you have two qubits, something called Q1 and Q2, let us say separated by some large distance, maybe 300,000 kilometers speed of light in 1 second. The moment you measure this and this comes up, this has to come down. And if this happens, it's as if there is some communication happening between both of them, right? Because it is going top and it is telling it that, ha, I have gone up, so please go down, please measure down, and now you measure this, you kind of measure it down, right? The spin comes down, the spin comes up, the spin comes down, and this happens instantaneously. The problem is, if this happens, Einstein's special theory of relativity says that nothing can travel faster than light. Special theory of relativity, C is the upper bound. So then how is this possible? This basically violates special theory of relativity, right? This violates, because here you would assume that something travels faster than light, because those two qubits can be at the ends of a galaxy, and still if they are entangled, it should instantaneously change. How is this possible? This is nonsense. So this is what the EPR paradox was. He said, if quantum entanglement is true, as given out by Niels Bohr and Heisenberg, then it should violate the special theory of relativity. And special theory of relativity, we know, and Einstein proved that there is a physical limit to how fast something can travel, which is the speed of light. So nothing can travel faster than light. Hence, this definitely whatever it is cannot travel faster than light, and hence this is nonsense. But this is not really true. Superposition and entanglement is just he said the quantum theory is not complete yet. He actually called it spooky action at a distance. That's the word he used. He said it's a spooky action at a distance. He basically said this is not right. Okay. So everybody gets the EPR paradox. Why is this a paradox first?
Yeah.
Okay.
And all of this again boils down to the fact that Einstein felt about the hidden variable theory, that there is something hidden.
Who was the explanation he gave for this? Because he said this is not possible. The quantum mechanical view, which is based on superposition, is not possible. And he gave his own explanation. The own explanation became known as hidden variable theory. So his explanation was, there is something inherent in these qubits, which makes it go either spin up or spin down. So if you knew that information, you can actually predict if this will be, because last time in superposition, all the experiments we did, what did we find out? That we actually cannot predict. We took color and hardness examples, but forget that. But actually what you said is, there is no way, it is random. What happens is completely random. Okay, randomness is an intrinsic part of quantum particles.
Yeah.
But Einstein said, hidden variable theory, what did he say? He basically said, there is something else in these qubits that we can't measure now. We don't know what it is. But if you can measure that, you would know whether it will go spin up or spin down. So if you could measure that, even beforehand, you already knew whether it will go up or down. So there is actually no need of any information passing. That information is locally available. It can locally decide whether it has to go up or down.
No.
Because that information is, see, this is called non-locality, quantum non-locality, right? Entanglement is non-locality, which is two particles are depending on each other, which are not local to each other, which are separated by any amount of distance, the same thing should hold. But Einstein says for that to happen, something has to flow between them. And that something cannot flow faster than speed of light. And that is why it is a problem. Because and this is the second problem. The first problem yesterday we talked about, right? That polarizing experiment, quantization itself created some problem for Einstein. But this was the death knell. They basically said that because his special theory of relativity was being challenged. This was 1935. He had already won his Nobel Prize. Special theory of relativity was out. General theory of relativity was also out by that time. Right? And there is this Danish guy and a German guy who were proposing that all of this is nonsense. So that was his thing. So hidden variable theory is nothing but there is some variable in here that we don't know how to measure at this point. But if we could measure that, we could know what the spin is, and hence spin is a local information. Nothing needs to travel, and so all of this is fine. Get that clear?
Yes.
Yeah, Madhu, Anik, Dheeraj, everybody?
Yes, sir. Yeah.
Okay,
Yeah.
good.
Yeah.
Because this is something, sometimes a little subtle, people can get confused, so that's why. Okay, good. So now we have this. For 30, 35 odd years, both interpretations were in vogue. Some scientists believe Niels Bohr, where he said, it's completely random. There is no hidden variable. Okay. There is nothing even called spin till you measure it. But once you measure it, it instantaneously changes. How it happens, we don't know. It is what he called nature's magic trick. Okay. But that is how nature works. And Einstein said that's nonsense. God does not play dice, right? His famous statement. God does not play dice. And he said, God does not play dice. There is no randomness. There is something hidden, which if you can measure, you would know. Just that we don't have the technology to measure it. Now, in 1965 comes according to me, probably this top 10 experiments in physics ever conducted. Not just physics, maybe all over science, by John Bell. He was an Irish physicist. It's a tragedy that he never got the Nobel Prize. But John Bell in 1965 finally proved that hidden variable theory is wrong.
Newton didn't get any Nobel Prize in medicine.
Yeah, and Newton was before Nobel Prize, but yes, so John Bell definitely proved it. Of course, in his time, he could not, it was a thought experiment for John Bell. That experiment got conducted later on. In late 60s and early 70s, that experiment was actually conducted. But he had constructed the thought experiment and he had proved it from thought, but the actual experiment happened later. 1965 is also another interesting year if people are interested. It was the year that Richard Feynman got his Nobel Prize. And Richard Feynman in his Nobel Prize lecture actually said that, and he got his Nobel Prize for his work on quantum mechanics. He said, now I can safely say that nobody understands quantum mechanics. Because I was supposed to be the guy given the Nobel Prize for doing it, and I for sure don't understand it. So I don't know who else understands it. So Feynman, a famous speech that people hear about Feynman, right? Now there is one other thing, so we will go into John Bell's experiment and try and understand it. This is a little subtle, okay, so you got to pay some attention to this. This is, see, and the way I am going to explain this is by taking bit of liberties, because the actual math gets very, very complex, okay, you don't need to get to the math. We're going to look at the intuition, but this is what it is. The experiment is this intuition only. But we'll get it, okay? Now the thing is also is that you should remember, we talked about spin. Now, spin, you can measure spin in any direction, right? So for example, if you measure spin on the z-axis, okay, which is the top level, the z-axis, right? Then spin will either come up as up or down. 50% of the time it will come up, 50% of the time it will come down, right? Now, if you measure it in this direction, x-axis or x-axis, right? Now the spin is like this, and you are measuring it horizontally. So if you measure it horizontally also, you will get it some 50% chance. 50% it will come up and 50% it will come down. But here is the trouble. If you measure it at, let's say, some 60-degree angle. Now, if you measure spin along an axis, that is at an axis, then it will be, the probability will be proportional to cos square 60 by 2. Amplitude. Cos square, right? Horizontal. So it will be proportional to this. So that cos square theta by 2 is what this will, the probability will get proportional to, which is kind of an important thing. Okay. Root 3 by 2, so 3 by 4 and things like that, right? So this is 30, cos 30 degrees is root 3 by 2, and you can do that, right? So this is important. Okay, the probability of it up or down, because 60 degrees it's closer to up. So up will come more now. If you make it 30 degrees, it's closer to this. down will come more. So it depends on what you're talking about. If you make it 45 degrees, equal both again. So depending on the angle, and this is where it gets really funny. The way because it does not actually, spin never gets measured at an angle. The spin will always come up or down only, but the probabilities will vary. See, in any classical mechanics, how do you do, or in any classical system, if you have two vectors, these are called basis vectors, or this, where the span of this is the entire two-dimensional space, right? Any vector here can be written as some linear multiplication of this and this, correct? So that is how you kind of do, right? Anything can be written as something ax hat plus any vector in this space can be written as a linear combination. Right? Yeah, some people say I hat and j hat. You can kind of write whatever you want, doesn't matter.
Then it is represented basis vectors.
Yeah, so I hat and j hat, whatever. So you can write a I hat plus b j hat if you are comfortable with that. But essentially, what I'm saying is this span is the entire space, right? So classical mechanics tells you if you measure something like that, the answer will be a combination of that. But in quantum mechanics, the answer is not a combination of that. The probability of it occurring will become, so it is like saying this will come x with a probability of this. Instead of saying that the answer itself will be this vector, the answer will not be this vector. The answer will still be this vector or this vector only, but the probability of if you measure it will depend on what these are. Which is a fundamental difference between classical, because in classical it is just a linear combination. You will say if somebody is running, I don't know, if something is going this direction with some component, this direction with some component, so the force will be in this direction with some component. Right? If there is some force like this and some force like this, the equivalent force will be like this. That's what entire classical physics is based on. Whereas in quantum, you are saying no, the answer will still be either on this side or this side only. The probabilities will vary depending on what is the angle here that you are measuring it on. Okay, which is a fundamental difference. You just have to understand it. Okay, what else is there before I get into? Yeah. So now, how did John Bell do his thought experiment first? He said, let two particles be simultaneously created out of some energy. Let there be, like God said, let there be light. Let me give some energy and two particles are created out of it, two photons. Okay, I kind of I don't know, take a flashlight and show it to something. And then I put some energy on, so two photons will be emitted. Now those two photons, once they get emitted, one photon has to have a positive up spin and one has to have a negative spin. Right? Because the total angular momentum of the universe needs to be conserved. You cannot have same, you cannot have. So this is the first step. So you have now two photons, one with a positive spin and one with a negative spin. He said, let me make two detectors now. Okay. And this is the interesting bit where John Bell starts having fun. Call this detector A. Call this detector B. These are the directions in which you will measure the spin. So one is straight forward. And these two are at 60 degrees with each other. This is like an equilateral triangle. Imagine them to be the sides of an equilateral triangle, right? Each is 60 degrees with the other. This is 60, this is 60, this is straight. Now, He says, case 1, let us imagine that there are hidden variables, that these particles actually have some hidden variables. So you can think about hidden variables like having some sort of plan. Like basically, before they are born itself, they will decide to each other what we will be, right? Something like that. Some variable that can predict what their spin will be. So you are assuming, let's imagine Einstein's scenario. Let us say hidden variable theory is right. And these things have some internal plan. Those spins somehow know what they will end up being when they are measured. Those photons know what their spins will be when they are measured. Let us imagine that. What can be a Okay, sorry about that. Okay. Okay, one other assumption is the directions will be chosen randomly in each one of these detectors as they are being measured. Okay, so anytime any direction can come, they will choose the directions randomly. Okay, and the two detectors are independent. So it is not like one detector is being influenced by another detector. Another two assumptions that you are making. So one plan could be one hidden variable can say, let us say this is qubit 1 and this, let us it be qubit 2. This experiment is a little complicated, champions. And they say the way the decision is made is qubit 1 can say, irrespective of wherever I measured, I will always, let's say plan 1. Plan 1 will be qubit 1 will always be up, and qubit 2 will always be down. Let us say it is some plan that the qubits have made between each other, because there was some hidden variable. Some hidden variable is such that it is there. Okay, that is one plan. There can be another plan. Plan 2, this can be a little bit more, but let's say for qubit 1, it may say I will be up. Maybe let us call these directions 1, 2, 3. Okay, it will say up in first direction, right? Something like this. Down in second direction, always, and up again in third direction. Similarly, if you look at qubit 2, it may just do the ulta. The plan may be down in first direction, up in second, and down again in third. Let's say they have made a plan like that. This is hidden variable theory. We're talking about hidden variable. So qubits are communicating. They are, before they are born itself, there is some variable in them that lets them choose something. That's what Einstein said, locality of information. All the information required for the qubit to become either up or down is inside itself. Intrinsic, some intrinsic property that does it. You don't need, there is no communication required. And that is the same rule, right? If you have a left glove and a right glove, either when you measure it becomes, quantum mechanics says the glove is neither left nor right. The moment you measure it, it becomes left. And if this becomes left, something else becomes right. Einstein says no, the glove was always left or right. Only when you measured, you knew it was left or right. So that is what, so it's very subtle, right? So the glove was always left, you knew it was left when you saw it, is one interpretation, which is Einstein. Niels Bohr said the glove, when you did not see it, was neither left nor right. It was something else. When you saw it, it randomly became either left or right. And then as soon as it became left or right, something else also became the opposite direction when they are in time. So actually, if you look at it, Einstein's explanation sounds more reasonable. Because that is how we are used in the world, right? How can you have reality and so on? But anyway, we know the final answer, unfortunately, now who won, who lost. But we will have to see how John Bell proved it is fascinating. Okay. So he says this is another plan. Let us say. Now, all other plans that you can come up with. For example, you can say, I will go top in second direction and then third direction and first direction. You can keep doing this, right? You can do various permutations of this. All of those will be equivalent to plan 2 only. Mathematically, they'll all be equivalent to this plan. You can do many other plans on this. You can say, okay, I will start from third, I can start with second, I will do whatever. You can do any combinations of this. But all other plans, and we won't get, if you write the equations, they will all be some 8 things, 2 power 3 or something, different combinations you can do, but they'll all be equivalent. So these are the, one plan is simple, the second plan is alternating. And why we are doing it, the way we will conduct the test is, we will detect in 1, we will detect in 2, and wherever the spins will come different, we will be recording them. Because essentially, entanglement says the spins have to be different. So we will record the number of ways, number of times the spins will be different. Because we are, if you are measuring in one direction, it will be 100%, but we are measuring in 3 directions, so it will not be 100% actually. Because in this direction and in this direction, it will be probabilistic depending on whether this is closer to the up or the down thing. So it will not be 100. If it was just one direction, then it didn't matter. The answer was simple. In fact, you couldn't detect why it was up. Both will say 100%, 100%, and both results you will get 50, 50, 50, 50. You can't say anything. But because you are doing it in 3 directions, that's the genius of Bell. There is actually randomness, and we'll get to the math behind it. So these are equivalent, right? So all the others are equivalent. So if you do it in plan 1, under plan 1, 100% of the time they will be different. Correct? Because whatever I measure qubit 1 in detector 1, it will always come positive. Whether I measure it in this direction or this direction or this direction, it will come up only. And qubit 2 has decided it will always be down. So in the other detector, when I test qubit 2, it will always be down. So under plan 1, it will be 100%. 100%, they will be different every time that you measure. No problem up till here?
Yes.
Yeah.
So now comes the second part. Now the second part. Now let us say in second plan, under second plan, you are measuring it in detector A, and let us say it came up. You measured in this first direction and it came up. The first direction should come what? 1/3 of the time, right? Because you are saying you are picking up directions randomly. And now the second qubit is measured in the second detector. Okay. If it is measured in the other 2 directions in the second detector, that will come 2/3 of the time. Because in the second detector, this is detector A. In detector B, if I write here, detector B, the second one will come 2/3 of the time at those 2 angles. They will come 2/3 of the time. And it will be up 3/4 of the time. Because cos square. So 3/4 of the time the result will be up. So if you say 2/3 by 3/4, half times it will come up there, and 1/3 of the time it will come up here. 2/3 of the time it will, again, 2/3 into 3/4 or whatever. So basically half the time it will come up and half the time it will come up here. So the answer is, the particle contains, which should be different results, right? So if you actually add it, so, and plan 1 and plan 2, if you kind of take, the plan 1 will be 100% of the time. Okay. Particle B, let me just see this. This calculation is always a little weird. Okay. If the particle is going to other directions, it makes 60 degrees. It should be top 3/4. The particle B will give half of the time. So 2/3 into 1/4, which is 1/6 of the time. How is it getting 2/3? Yeah, so it will be down 2/3 into 1/4. It will get down by 2/12, which is 1/6. 1/6 of the time it will come down. In this 2/3, plus in the top one, it will be 50%. Okay, let me do the calculation again. I don't want to confuse you. This confusion will be finally in under Einstein thing, it will come 5/9. Let me see how you. Okay. So let us see. Qubit 1 will get 1/3 times. It will get 1/3 detector A. It will come top in first direction. That will come 1/3 of the time. So if you look at detector B and you want to see detector B will be what? Down in first condition, right? It says down in first. So that is again 1/3. So down is 1/3 down. Okay, because this is qubit.
Only first. Okay, that's only on first.
First, yeah. If you just imagine this, we want to measure the things, right? How many times they come. So 1/3 it will come up, 1/3 it will come down. That is pakka in the first. Here between the two, when you measure, half the time again it will come up. No, this is wrong. Detector B, this is why this Bell's experiment is very, very funny. It will come 1/3. So, okay. If you look at detector 2 will be, it says what? Qubit 2 will be second and third. So those two angular things, it will come 2/3 times into 3/4 it will come because it is whatever. And so this becomes 1/2 times it will come down. So the other 1 minus 1/2 time, the other time it will come up. You just have to take it like that, I guess, because the other, and instead of calculating the up probability, I think we just did 1/2 minus 1/2. The other half it will come up. And if you add it up, if you add plan 1 and plan 2, because plan 2s will be many more, then this will be 8 different plan 2s. 2 cube, 8 different plan 2s, and only one will be plan 1. So if you add it up, it comes to 5/9. It will come. The probability of times that they will be different. If you do the math, it will come 5/9 because the total will be 9 cases. Total will be 1 plus 8. Total will be 9 cases. Out of 9 cases, 1 is definitely always different.
You have listed only 6, but 2 up and 2 down can happen.
Yeah. All of those, because finally you have 3 directions, each one has 2 up, down, up, down, up, down. Any combinations you do, it is 2 power cube equals 8. 8 different combinations you will have here in plan 2. Whatever combinations you take, because the order doesn't, it matters, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3. You do, it will be 2 cube 8 because each one has only 2 things. You can do either up or down. You can do it 3 ways. So the total will be 9 different things, plan 1 and 8 of plan 2. So if you do the math, I think, which probably you can do, or maybe I can do at some other time, I have to sit down and enumerate all of these. If you enumerate all of this, you will get it 5/9 times. 5/9 times you will have to get different. Okay. In actual experiment, you only get 50%. In actual experiment, when you do this experiment, you do not get 5/9. 5/9 is greater than 50, right? It's 55% or something. but actually you get only 50% if you do the actual original experiment. And we'll see how quantum mechanics explains that the answer is going to be 50% and not 5 by 9. And that is how Bell's inequalities get violated in quantum mechanics. And that is how Bell proved that there cannot be any hidden variable, that there cannot be any plans. Though there are still people today who say Bell's experiment itself was not right. So there are still skeptics. I'm not saying that it is proven, but for all practical purposes, it's now seen that it is not really like that. And we can probably see how quantum mechanics or whatever kind of interprets these results. Say quantum mechanics is very simple. Quantum mechanics will be 50% because you don't know till you measure. So if you don't know till you measure, and everything is random, and within each random thing, whichever you pick up, it is 50%, 50%, 50%, 50%. So the whole thing will be 50% if you actually do it in a quantum mechanical way. Okay. So quantum mechanical is easy. This is the difficult part. This calculation, sorry, I forgot how exactly to do it, but if you do it, you will get this 5 by 9. Okay, which we can check out. So this is how they kind of proved it. John Bell proved it, that this is not really hidden variable, but this is actually something to do with something else, and that something else is what we kind of take today as quantum entanglement, and then we say whatever. No, but there is still a problem. And the problem is how can these results be interpreted? See, if you really think about it, see one more way to think about it. This calculation, if I have time next class, I'll go through the calculation again. I just have to go back home and this weekend spend an hour trying to do it. See, here is the problem, right? If you see, there are two bits which are entangled, and this is the great Alice and Bob story. Okay, there is Alice and there is Bob. You'll keep hearing this story everywhere in quantum mechanics. Alice and Bob, and then they have two qubits which are entangled, and now they are taken all the way away and whatever. And so once he measures something, he knows that the opposite is measured something else. So can they use that to actually communicate? Right, that is the point, because the whole point is quantum communication. Can you use this to actually communicate something between people? Because if you could do that, then you can communicate at a speed higher than speed of light. Because these are two quantum bits that are farther away, a million miles away, and you measure one, you know the other. But the whole problem is, whoever measures this, Alice or Bob, doesn't also know what the result will be beforehand. They will only know, yes, they know it is going to be the opposite, but the opposite of what is random. Because they don't know that it's going to be down. They don't know it's going to be up. They are going to know it is between down and up. If I get down, Alice has got up. I know only that much, but I cannot know that. I cannot predetermine that, okay, this time I will get up. Then you get, because then you can communicate, but you can't do that. You can measure, you can only say, I don't know what I will get, but whatever I get, she will get the opposite. That is the only thing you can say. If you could say that you will get down here, and if you know that you will get something else there, then you can communicate, because then you actually know what you are going to get here. But here you cannot communicate anything. You can only communicate if they match up again later and compare notes and say, oh, for me, down meant this. But if they have to meet up anyway, that means a classical bit has to be sent. A classical, if a C bit has to be sent, you lost. Because then it can't travel speed of light. No, it can only speed of light if this entanglement can happen. And there is a lot of, so quantum communication theory now, at least we believe, see, none of this is 100% sure, because people are still researching, is we cannot actually communicate using this. And that this doesn't violate special relativity because this is random. If this was not random, maybe there was a way to communicate. Okay, and that is kind of the big insight here. For us, how is this useful? How is quantum entanglement useful in quantum computing? It is very, very useful. Because at the end of the, see, for us, what is the problem here? See, when you talk about quantum computing, what is the problem? We have to start from a classical world, do quantum, Within quantum, you have to do computations. Within those computations, now you will typically get a range. Because a quantum will not give you an answer, it will generally give you a range. Now within that range, you need to translate it back somewhat into the classical world again for us to be able to use the result. Because if you want to multiply 2 into 2, how will you do it? 2 into 2, you know, is 4. So 2 into 2, you have to convert it into some superposition state. Okay, back here, do some answer, do something. The answer you will get is, with some high probability, this will lie between 3.9999 to 4.010, something like that you will get. Because finally you will get some probabilities in the quantum era. So those probabilities, you have to convert it back into some classical method to say, oh, I'm 99.99% confident that this is equals 4. That is how this will happen. Now, the whole problem is, when you have superposition, you have what? You exponentially increase your computational capability, because a bit is not now 0, it is 0 and 1. So you can do the calculations imagining it is 0, and you can do calculations imagining it is 1 at the same time. So that is the advantage that it gives you, right? So that's what we said, right? When you do the tensor product, the state is exponentially, it includes everything, and which is why you do that. Now, but this is not good enough. Now, if you entangle these two bits, then you have a state of 4 now. Not just 2, you have a state of 4 different things, and all of them can parallelly compute because they are all entangled. And the advantage is, finally, when you measure, you collapse one, the range gets immediately down. You understand what I'm saying? What's the advantage of entanglement, and why do we entangle qubits when we are doing quantum computing? Because now you have if you entangle 100 bits, let's say you are entangling 100 bits, then each bit has 2 states. You have all those states available for you, 2 to the power 100 states available for you to do the calculation. But the advantage with entanglement is, finally you measure and you say the 100th bit is something, then all other bits collapses. Down, up, down, it will just collapse. Because once that is there, everything else has to be the opposite, the opposite, the opposite, the opposite, the opposite. So you are able to finish off that calculation. Normally, if you have to do that calculation, you have to search through an array or a list of whatever, that much size to say what are all the applicable values. But in quantum, you don't need to do that. You just measure one, everything else collapses. That is the advantage. That is why we worry about entanglement, and we need entanglement to work. Hope I was a little clear on why we are so bothered about entanglement and understanding entanglement.
In terms of computing.
Computing, in terms of computing. Otherwise, naturally, if you're studying quantum mechanics, of course, without studying this, how do you study anything? Okay, you need to study this. But our goal here is, we are not trying to do a physics class here. In a physics class, we'll get into a lot more detail on any of this. Right now, we're just conceptually trying to understand this. Third, next class, we'll conceptually understand the wave function. Once that is over, we will get to computing again. Okay, because I want to get us, because there is a huge space, and over the next 2-3 years is going to become mainstream. The idea is not quantum in itself, right? See, what does quantum can do? You will have to merge it with classical computing, and see what can it do. If you really think about it, for example, if you are doing any optimization problems, okay, what is the problem with optimization problems today? If you have a traveling salesman problem, what is it that we struggle with traveling salesman problem? The number of options are so huge, the compute space is so huge that we cannot classically solve it. There is no way to classically solve a traveling salesman problem, right? You can only do approximations and approximations. Now imagine, out of whatever, 2 to the power 1 million or some options, you can do quantum computing and cut down this range to the next 1,000 solutions. You know the answer lies here. Then you can do classical to just roam through the 1,000 and finish it off. See, quantum computing will be useful in doing that. It will be useful because you will not get one solid answer, but you don't need an answer. You only need a pruned out range that you can use your classical computing to finish off. Same way with machine learning. Okay, when you're trying to fit trillion parameter models, what is the issue that you are facing? You cannot really converge. That convergence doesn't mean anything. In such high dimensional spaces, it doesn't mean anything to converge, frankly. With something like quantum computing, you can cut down the dimensionality very, very quickly into something manageable and solve the problem there, because you know the solution lies in this part of the problem space. Right? So today, that is how we struggle in machine learning, right? You take your inputs, you encode. It becomes your input encoding space. And then you try and fit a function in that encoding space. And then you try and put some probability threshold to change it into an output space. Yes. Now, all of these spaces in such high dimensional spaces, that actually nothing is interpolation. Everything is extrapolation. And everything is, I don't know, finger in the air type. There is no way to guarantee any ranges in those sort of dimensional spaces. If you can cut it down dramatically using quantum computing to a certain part of the problem space. For example, you know, your input space can be, you know, if say ideally what, if you have a 200 by 200 pixel space, what is it? It is 40,000, right? It is 40,000 pixels. 40,000 or 4,000? 40,000. It's 40,000 pixels, right? Now, in this 40,000 dimensional space, what are you trying? So 40,000 dimensional space, now you have to encode this input. Okay, in a 40,000 dimensional space. Now that encoding, most probably now, how will it encode? How will the neural network encode? It will randomly put some encoding, and then using some sort of loss function, it tries to move that a little bit here, there, and hopefully it will learn a representation which minimizes the loss function. And then you say, that latent representation is a brilliant latent representation of your input data. This is what we're doing right now. Imagine in this 40,000 pixel dimensional space, ideally speaking, there will probably be some small 10 by 15 or 15 by 15 space, where actually the encoding, if you do it in that space, the answer will come. That is the perfect space. But to search for that space, a lot of times you can't search for it, and even the search is so prohibitively expensive to do it. And this is 200 by 200. That is nothing. If I give you 4K video, then you're done. It's a 16 million dimensional space. So how are you going to search for this? So quantum computing will help you, because you can quickly get through the range. And you can say, hey, there is this 50 by 50 place where the solution will lie. Okay. Once you get that, it's easy to run. Sorry, man, I digressed a bit on this, but hopefully I just want to make sure you understand why I am trying to bother you with all of these other things before getting into coding.
Yeah.
Okay. So, guys, did that help?
Yeah, sir.
Yes, sir. Yes.
Okay, so that is what that is. Any questions, anything you want to ask on this? I don't know. Next time we will discuss a little bit on wave function. Yeah. The wave function is also important. Yes, Dheeraj.
Initially, when the news came out from IBM, there was a video explaining a coin toss game. Right?
Yeah.
Hello?
Same thing, right? A coin toss in a classical bit, head or tails. In a quantum bit, it's a superposition.
I lost. I was saying that there was a coin toss game that was given by IBM, the computer.
Okay.
Quantum computer.
Yeah, I'm sure there are now all sorts of things. There are actually, I received a paper from somebody to review some work on NLP that they have done using part of it on the quantum computing, especially the self-attention layers, right? Because exactly what I'm saying, self-attention layer is a problem layer. Right? It's actually a stupid layer if you ask me. The only problem is, unfortunately, people get excited. So what is self-attention layer doing? If I say, I like the cat because whatever, because it is black. Now let us say this is the sentence. What does self-attention do? Self-attention takes this dot product, then it gives an array of dot products, all of these dot products. Then again, it will do this again, and with everything else again. So it is a very inefficient algorithm, right? Self-attention is just It is saying, I want to know how everything is related to everything else. Yes, extremely stupid in that sense. There is no intelligence in this. You are just doing that over and over and over again across huge corpora. And then finally, you are doing some sort of softmax function on top of all of that. Okay, to say, hey, I occurred with that many number of times, so the dot product somehow looks to be brilliant. So I'm going to say I and the are very, very whatever important or some bullshit like that. So that's what they are actually doing, right? There is no So imagine something like this in a quantum world becomes so much nicer, because all of this is just one function call. If you can encode if you can entangle your bits properly, it's just one call, and you can finish it off. So that is a huge win if you are trying to do any such functions, any such thing. Self-attention is a classic sort of use case for quantum computing in ML. Anything like self-attention, right? Anything that kind of does this repeatedly again and again, and also naturally for us, happily, the inner product. See, one other thing you guys need to understand, when you talk about physics or machine learning or anything, why does linear algebra keep coming in all the time? You'll be cursing why Srini always talks only about linear algebra. See, if you have a vector, see here is the space, right? You have a vector. Okay, everything is a vector space. So not everything, but not at least in machine learning. Now, what can you do to this vector? There are only two things you can do to this vector. Either you can scale it or you can rotate it. There are only two things you can do to a vector, right? What else can you do? There are only two things you do to a vector. This is, what is this? Scalar multiplication, right? So if V is a vector, AV is this. What is this? Some matrix multiplication, where you are trying to rotate the vector in space. Okay. If you don't want to do this, what do? Go frequency. If you go frequency, you don't need to do this. You don't have too many options here. Either you take it in space and you do linear algebra on it, or take that space-time into frequency components and simply do some discrete Fourier transform or some Fourier transform on it to kind of get the components out. The only two things you can do. Correct? Because here it's very simple. This is a vector, you rotate it, the basis changes maybe a little bit. Right? Orthogonal case, because it's the basis changes a little bit. Once you change this change of basis is nothing but all of your neural networks, representational learning. You're basically changing the basis a little bit. You change the basis to frequency, that's a whole another world. That's Fourier transforms. Okay. So you have to So I'm saying it's very easy if you understand the basics of what you're trying to do, rather than get caught up in all sorts of fancy things and this and that. Finally, there is nothing.
Essence of linear algebra,
exactly.
Clearly gives the visualization of how this whole works.
Yeah, exactly. Go to the 3 blue, 3 blue, 1 brown. Brilliant. Explain.
Essence of linear algebra, complete playlist.
Okay. So see the playlist. Finally, you just see. When I was young, we used to handcraft this. Now we do neural networks to do that. That is the only difference. There is actually no other difference. Okay. So that's it. So if you have a vector V multiplied by a matrix, you get some V dash, right? That's it. If this V happens to be displacement, this becomes vector. If this is displacement, then you multiply it with this thing, it becomes some quantity in space time. Now if you differentiate with respect to dt, it becomes velocity. Basic calculus and basic linear algebra done. Nothing else you need actually. That is all that there is.
There is other playlist as well, Essence of Calculus.
Exactly. Essence of calculus, essence of linear algebra. I know you guys have done it, but if you have not done it, spend as much time as you want there only. Nothing else you need. If you understand that, anything I tell you will be very, very simple. You can close your eyes and imagine. See, all of the thing is like this only. If I want to measure the temperature in this room, but see, one thing I'm saying, and how much time do I have? I've probably gone through time. If you have 2 minutes, just listen to this one thing. It's useful. See, there is this room, and there is some temperature in this room. Let us say I want to measure the temperature in this room. Okay, let's say I want to measure the temperature in this room. We are somehow thinking that we can do it using computers or something. So, which basically means you can digitize that information, right? You can discretize that information. How do you discretize that information? In fact, I can create a grid of this room, and I can create a grid, and I can make them, and I can divide it into a grid such that, for example, each grid is so small to fit only one molecule. For example, then each grid will have what? Either a 0 or 1. Each grid will have a 0 or 1. So that's it. The entire state of this room in terms of air can be written. That's all. And then how do I understand how, if I want to understand the temperature is what? Movement of molecules. So I just draw a million of these at each time instant and draw the same rules of moving between configurations. I have got temperature. That's all. That's all that there is. So you take those and you integrate, get it for the whole room, you differentiate, you get it for each time slice. It's as simple as that. You don't have to worry about. Finally, we just discretize. We just have to discretize at the right level. That's it. You can measure anything in the world. That is why computers work. Otherwise, why can zeros and ones represent anything? The fundamental question, right? But we can represent with anything because I can just divide it into a grid. And then finally, it's all right. Sorry about it, guys, and thank you for your time.